No communication theorem. In physics, the no communication theorem or no signaling principle is a no-go theorem from quantum information theory which states that during measurement of an entangled quantum state, it is not possible for one observer, by making a measurement of a subsystem of the total state, to communicate information to another observer. The theorem is important because in quantum mechanics, quantum entanglement is an effect by which certain widely separated events can be correlated in ways that suggest the possibility of communication faster than light. The no communication theorem gives conditions under which such transfer of information between two observers is impossible. These results can be applied to understand the so-called paradoxes in quantum mechanics, such as the EPR paradox or violations of local realism obtained in tests of Bell's theorem. In these experiments, the no communication theorem shows that failure of local realism does not lead to what could be referred to as spooky communication at a distance, in analogy with Einstein's labeling of quantum entanglement as requiring spooky action at a distance on the assumption of QM completeness. Informal overview. The no communication theorem states that, within the context of quantum mechanics, it is not possible to transmit classical bits of information by means of carefully prepared mixed or pure states, whether entangled or not. The theorem disallows all communication, not just faster than light communication, by means of shared quantum states. The theorem disallows not only the communication of whole bits, but even fractions of a bit. This is important to take note of, as there are many classical radio communications encoding techniques that can send arbitrarily small fractions of a bit across arbitrarily narrow, noisy communications channels. In particular, one may imagine that there is some ensemble that can be prepared, with small portions of the ensemble communicating a fraction of a bit. This, too, is not possible. The theorem is built on the basic presumption that the laws of quantum mechanics hold. Similar theorems may or may not hold for other related theories, such as hidden variable theories. The no communication theorem is not meant to constrain other non-quantum mechanical theories. The basic assumption entering into the theorem is that a quantum mechanical system is prepared in an initial state, and that this initial state is describable as a mixed or pure state in a Hilbert space H. The system then evolves over time in such a way that there are two spatially distinct parts, A and B, sent to two distinct observers, Alice and Bob, who are free to perform. The question is there any action that Alice can perform on A that would be detectable by Bob making an observation of B? The theorem replies no, lies no, lies no. An important assumption going into the theorem is that neither Alice nor Bob is allowed, in any way, to affect the preparation of the initial state. If Alice were allowed to take part in the preparation of the initial state, it would be trivially easy for her to encode a message into it. Thus, neither Alice nor Bob participates in the preparation of the initial state. The theorem does not require that the initial state be somehow random or balanced or uniform. Indeed, a third party preparing the initial state could easily encode messages in it received by Alice and Bob. Simply, the theorem states that, given some initial state, prepared in some way, there is no action that Alice can take that would be detectable by Bob. The proof proceeds by defining how the total Hilbert space H can be split into two parts, Ha and HB, describing the subspaces accessible to Alice and Bob. The total state of the system is assumed to be described by a density matrix S. This appears to be a reasonable assumption, as a density matrix is sufficient to describe both pure and mixed states in quantum mechanics. Another important part of the theorem is that measurement is performed by applying a generalized projection operator P to the state S. This again is reasonable, as projection operators give the appropriate mathematical description of quantum measurements. After a measurement by Alice, the state of the total system is said to have collapsed to a state PS. The goal of the theorem is to prove that Bob cannot in any way distinguish the pre-measurement state S from the post-measurement state PS. This is accomplished mathematically by comparing the trace of S and the trace of PS, with the trace being taken over the subspace HA. Since the trace is only over a subspace, it is technically called a partial trace. Key to this step is the assumption that the partial trace adequately summarizes the system from Bob's point of view. That is, everything that Bob has access to, or could ever have access to, measure, or detect, is completely described by a partial trace over HA of the system S. Again, this is a reasonable assumption, as it is a part of standard quantum mechanics. The fact that this trace never changes as Alice performs her measurements is the conclusion of the proof of the no communication theorem. Formulation. The proof of the theorem is commonly illustrated for the setup of Bell tests in which two observers, Alice and Bob, perform local observations on a common bipartite system, and uses the statistical machinery of quantum mechanics, namely density states and quantum operations. Alice and Bob perform measurements on system S whose underlying Hilbert space is. It is also assumed that everything is finite dimensional to avoid convergence issues. The state of the composite system is given by a density operator on H. Any density operator S on H is a sum of the form, where T and C are operators on HA and HV respectively. For the following, it is not required to assume that T and C are state projection operators, i.e. they need not necessarily be non-negative, nor have a trace of 1. That is, S can have a definition somewhat broader than that of a density matrix. The theorem still holds. Note that the theorem holds trivially for separable states. If the shared state S is separable, it is clear that any local operation by Alice will leave Bob's system intact. Thus, the point of the theorem is no communication can be achieved via a shared entangled state. Alice performs a local measurement on her subsystem. In general, this is described by a quantum operation on the system state of the following kind, where Vk are called Krauss matrices which satisfy. The term, from the expression, means that Alice's measurement apparatus does not interact with Bob's subsystem. Supposing the combined system is prepared in state S and assuming, for purposes of argument, a non-relativistic situation, immediately with no time delay after Alice performs her measurement, the relative state of Bob's system is given by the partial trace of the overall state with respect to Alice's system. In symbols, the relative state of Bob's system after Alice's operation is where TR H H H H A backslash display style backslash operator name TRH is the partial trace mapping with respect to Alice's system. One can directly calculate this state. From this it is argued that, statistically, Bob cannot tell the difference between what Alice did and a random measurement, or whether she did anything at all. Some comments.